This is Jonathan Gertson. I'm taking ENGR 459, Advanced Electromagnetism. This is for assignment 4. I've been tasked to take a look at Maxwell's equations and how they can be solved using a wave solution. This course is being taught by Dr. Kenneth Chow at the University of British Columbia. So let's start with a quick overview. This is intended to go from Maxwell's equations, his famous equations for electromagnetism, and take them over to a plane wave solution, which allows us to describe electromagnetic plane waves. Now, assuming that you don't know how to make that jump in one step, we're going to take a bunch of little steps. Starting out with, what is a wave? We're going to answer that question. We're going to say, how do I describe a wave using math? And then what does a plane wave even look like? And then now that we've got that information, how do I get from Maxwell's equations over to plane waves? Once we've got all of those things combined, we will have a solution for Maxwell's equations using electromagnetic plane waves. And then we'll take a little step further and say, why is this a good thing? Why would we even want to do this? Let's begin by answering the question, what is a wave? So, a common description of waves is anything that you can surf is a wave. It's not quite true. I went and thought up a couple of things that you can surf on that are not waves, but it's neither here nor there. A better explanation of what is a wave is something that is time and space harmonic, which means that it repeats itself given enough time or given a movement in space. Take, for example, a buoy floating on the ocean with waves going up and down. If you sit on the buoy, which is a single point in space, the buoy will go up and down, and it will return to the same point after a given amount of time. That is time harmonic. It repeats itself with time. If you were going to do the same thing with space, you could say, well, if I froze the water and moved all the way over to the next wave crest, then I would come back to the same height. So that means that it's space harmonic. And you can go space harmonic in both directions, either forward or backward. Now, an important idea to catch on right now is how this relates to a plane wave. So imagine that you were looking flat down on the surface of the water. You'd be able to see that there are some crests and troughs in the water as the wave is traveling past you. Now, that means that it is going to be space harmonic in the direction that the wave is traveling. And along the top of the wave, assuming that everything is parallel, it's not really space harmonic. There's no change in the height of the wave, so we don't usually think about that. But in essence, this is a plane wave. Okay, let's describe a wave using math. In a three-dimensional Cartesian space with time, this function that we're going to assume describes a wave could have as many as 4 variables. But we want to keep it simple right now. So we're going to say that our function does not depend on y, does not depend on z, only depends on x and t. And why those two variables, why t at all, will be apparent later. So let's start with a function that everybody already knows and loves, cosine. We'll give it a space for some arguments, stick an amplitude out up front, give it a kx term for spatial dependence with x, omega t for a temporal dependence on time, and we'll add a phase term in it for later. So we've got an amplitude now out the front that we're using to describe this wave. We have a spatial harmonic term kx and a time harmonic term omega t plus that phase term. And that phase is just going to be used to describe if there's any difference between the spacing of the waves if we end up using multiple waves. We won't need it today, but it's important to know that it's there and why it's there. So trig functions are just one way to describe a wave. We can also describe it using Euler's identity, where we have e to the power of I theta is equal to cos theta plus I sine theta, where I is the square root of -1. It's the imaginary unit. Another way that we express these is that the real part of e to the I theta is equal to cos theta, and the imaginary part of e to the I theta is equal to sine theta. So we can use these terms and express our original formulation for a wave and convert it to an expression using Euler's identity. And the great thing about this is that because we have that constant term phi, we can just pull that out of the exponential. And once we've pulled that out, we can combine it with our original amplitude A and kind of hide our phase term in the amplitude, giving us a complex amplitude. Now, it's important to note that the A complex, or A tilde, sitting out the front, is not the same as our original amplitude. It has a phase hidden away in it. Finally, what we would say is that our original term can be recovered, and it can be recovered by saying that our original term is equal, or our original formula is equal to the real part of A complex times e raised to the power of kx minus omega t. Now this is a solution to the plane wave equation. It is one solution, not all of them, it's just one. And so is our original term. These are just different ways of expressing. All right, Maxwell's equations. They had to come up eventually, might as well do it now. So we're going to start by writing out Maxwell's equations. The first is that the divergence of the electric field is equal to the charge concentration divided by the permittivity of free space. The second is that the divergence of the B field, or the magnetic flux, is always equal identically to 0. We have that the circulation of the electric field is equal to the negative time derivative of the magnetic flux, and that the circulation of the magnetic flux is equal to the the permeability of free space times any electric current plus the electric flux going through the area. Now we're going to simplify this by assuming simple media. We are going to assume that there is no current, so J is equal to 0. We're going to assume that in simple media, all of our permeabilities and permittivities can be expressed using constants. So the magnetic flux density is equal to mu naught times mu relative times the magnetic field, and that the electric flux is equal to the electric permittivity of free space times the relative permittivity times the electric field. And this allows us to simplify Maxwell's equations and say that the divergence of E is always equal to 0, the divergence of B is equal to 0, the circulation of E is equal to the negative time derivative of the magnetic flux, and the circulation of the magnetic flux is always equal to mu naught times epsilon naught times the time derivative of the electric field. We simplify these a little bit further by taking all of the variables out so that we're only dealing with E fields and H fields. The divergence equations remain the same. The circulation of the electric field is now equal to mu naught times mu relative times the time derivative of the magnetic field. The circulation of the magnetic field is equal to epsilon naught times epsilon relative times the time derivative of the electric field. And we often simplify the mu naught mu relative and epsilon naught epsilon relative terms to simply be mu and epsilon. And those are Maxwell's equations in a nutshell. So now that we have Maxwell's equations, and we have an idea of what a wave physically is, let's try solving the most general form of the wave equation, which says that for any function phi, if the Laplacian, which you can think of kind of like a second spatial derivative, if the Laplacian of a function is equal to a constant times the second time derivative of that function, then it has a wave solution. Now this constant c out the front is not the speed of light, another common use for c, and I'm going to use c as the speed of light later, but this is not the same thing. This is just an arbitrary constant sitting out the front. So I'm going to begin using one of Maxwell's equations that we've modified for our own purposes, and it's the circulation of E. I'm just going to rewrite it over here. And then I would like to take the circulation of both sides, or del cross whatever I've got on each side. On the left, this allows me to exploit a matrix identity that gives me these two terms, one of which is the Laplacian of E. Now, we know that in the first term, where we have the divergence of E, we said earlier that in our simple media, the divergence of E is always equal to 0. So this term just kind of goes away and leaves me with the negative Laplacian of E. On the right-hand side, I'm going to exploit the fact that the del operator and the time derivative are both linear functions, and I'm going to switch places, pull the time derivative outside of the cross product. Having done that, I have a term now that is the circulation of H, and I can take that term and replace it with our third equation and say that that's equal to epsilon times the time derivative of E. Now that I've got that, combining those two time derivatives, I have something that looks very similar to a wave equation. I've got the negative Laplacian of E is equal to the negative of epsilon times mu times the second time derivative of E. Dropping the negative sign on both sides gives me a perfect wave solution, where my constant is epsilon times mu. And this is a wave solution. And if this is a wave solution, it means that we should be able to use other wave functions to describe the E fields, and we're going to pull over to the complex functions and the cosine functions that we were using earlier in order to make this description. So here I'm just going to run through a quick solution, the same process that we did to the E field, we're going to do to the H fields, to the magnetic fields. If you're following along with this, please note at this point that I did drop a negative sign, and I realize it right at the end, right about here. And I go back and change one of Maxwell's equations that we simplified for our solutions in plane waves. Just if you're following along, make sure that you catch that. So let's let our wave propagate in the x hat direction. That means that our complex E field is equal to some constant E naught tilde times the exponential of kx minus omega t, with the imaginary unit out the front, so that it's a nice harmonic function. We said earlier that the divergence of this field must be equal to 0. It was our simplification of Maxwell's equations that makes this necessary. Now, E naught can have components in the EX, EY, and EZ direction. If we are moving in the EX direction, it means that our EX must be equal to 0. And the reason that that must be true is that if the divergence of E is going to be equal to 0, and EX is non-zero, then we'll end up with some component forcing this equality to become untrue. So EX must be equal to 0. And likewise for HX, which means that we have no component of the electric or magnetic fields that are pointing in the direction of propagation. So what does a plane wave look like? How do we visualize this in our heads? We draw a set of axes, right-handed as per normal, and throw a wave on here, propagating in the y direction, and take an arbitrary step in the x direction. If we follow the same wave, we're going to see exactly the same pattern that we did at x equals 0 and at x equals an arbitrary amount. And in fact, any direction, any amount that we step in the x direction will result in the exact same values. So we end up with this sheet rippling through space that is infinite in the x direction, propagates in the y direction, and is defined in the z direction. Now, we won't use these coordinates for the rest of the video necessarily, because I prefer to work with x as a variable, but this is one representation of a plane wave. If you took a look at it crosswise from the x hat direction, then you would see it look just like an ordinary sine wave propagating in the y direction through space and time. And if you looked at it down from the z hat direction, you would see something similar to one of the first wave drawings, with troughs and crests and all of the orange lines I've just thrown in there for visual purposes. That's basically what a plane wave looks like. So what else can we learn from these expressions? Taking Maxwell's equation again, we can recognize that one side is a spatial derivative and one side is a temporal derivative. Recognizing that, we can break our complex plane wave into several components. And on the left-hand side, the exponential with respect to time is constant, and on the right-hand side, the exponential with respect to space is constant, at least with respect to the derivatives on the right and left-hand side. So we can pull those out on their respective sides, and then finish the derivative with respect to time on the right-hand side. The exponential e to the negative I omega t cancels out on each side and leaves us with a slightly simplified expression. Now, remembering from earlier that the divergence of both of these fields is equal to 0, we can expand them to show that there's an x, y, and z component, and note that the x component of both electric and magnetic field must be equal to 0, and that there is no field in the direction of propagation. Having recognized that the x components of the electric and magnetic field are 0, makes this next step a bit easier. We can fill in the cross product for the circulation with all the components and is 0. And remember that the x component of the magnetic field is equal to 0 on the right-hand side, which means that the x component of the circulation of the electric field must also be equal to 0. With this, we can finish the cross product and get the derivative of x for the Ez and the derivative of x of Ey. And we can take this derivative, fairly simply remembering that Ez and Ey are constants. And we can bring Ik down from the exponential in both cases and say that that's equal to the magnetic field expression we derived previously. Now, whoops, missed an I. Now this means that the I, the complex unit, cancels out on both sides, and so does the exponential with respect to Ikx. This leaves us with k negative e to the y plus ey to the z hat is all equal to mu omega and h naught complex, where h naught is still capable of containing multiple directional values. In this case, hx is 0 and hy and hz will be equal to what's on the left-hand side. Now this vector expression can be simplified to x hat crossed with e complex, and that's all equal to our right-hand expression. Now this gives us a really neat relation because it means that the magnetic field is proportionate to the electric field and directionally different by a cross product, but they're proportionate. That's really cool. We didn't know that before. I mean, we knew it before, but we didn't have mathematical proof for it exactly the same way. Now, grabbing a couple of other expressions, we're going to say that the speed of light is equal to 1 over the square root of mu naught and epsilon naught in free space. And from other resources, we're taking that k over omega, which is your spatial frequency over your temporal frequency, is equal to the refractive index n divided by the speed of light c. And n is equal to the square root of the relative permittivity and relative permittivity of whatever material is being passed through. With that, we can expand the expression of the electric field or the magnetic field slightly and come up with something that looks like this, which is still proportionate to the cross product of x hat and E naught complex. We've just run a substitution. These mu relatives cancel out, and we get an expression that looks like this. Now, this term, 1 over c mu naught, is termed as the impedance of free space, and it actually has a value of being equal to 377 ohms. This term is the relative impedance of a material, and we commonly combine these two parameters to be simply the impedance, 1 over eta. So now we can say that H naught complex is equal to 1 over eta times x hat crossed with E complex. Now, this can be generalized slightly further because E naught doesn't have to point in only the y and z directions, or in our case, only the z direction, which is something we assumed previously. We could have E naught pointing in any direction we wanted, and we're going to call that n hat. And this is also known as the polarization vector. What else do we know now? So we know that the magnetic field is perpendicular to the electric field. We know that the magnetic field is perpendicular to the propagation vector, and we know that all these things are perpendicular to each other, which is kind of handy. We know that E can have a polarization vector n hat, which means that it can be pointed in an arbitrary direction, so long as it is perpendicular to the propagation vector. And that means that for any polarized E and propagation vector k, we can determine the magnetic field both scale and direction. So can we make this more general? We specified an electric field dependent on x and t alone. But what if the electric field was not necessarily dependent on x? What if it was dependent on, say, r? Well, we could say that the electric field is dependent on the exponential of k vector and r vector dotted together and in the n hat direction. And that would make the magnetic field dependent on a constant ratio to the electric field with the same harmonic parameters in the direction that is perpendicular to the propagation vector and the electric field's polarization vector. Now this is perpendicular to both the propagation and the polarization. We have an impedance, we have a time harmonic element, we have a space harmonic element in both of our vectors. This is now able to be polarized, and we have a relative magnitude of the fields instead of having to define them explicitly otherwise. Okay, that's really cool. Let's just pause for a moment. We started with Maxwell's equations. They did not look anything like this. And we moved all the way to these complex wave equations, plane wave equations, that are dependent on space and time harmonics. They're related to each other in consistent and constant ways, and they're related to other material parameters through the complex impedance to each other. This is a really great and powerful way of using wave equations to help solve Maxwell's equation. So let's recap. We started with Maxwell's 4 equations, and then we assumed simple media to keep things constant and consistent in all directions, and then we did some math. We developed a complex plane wave solution to Maxwell's equations. And we did a little bit more math to see how these things were related, and we came up with these expressions relating the electric and magnetic fields and making them a little bit easier to work with, a little bit easier to define. And impressively, defined with respect to each other in both direction and magnitude. This is the plane wave solution to Maxwell's equations, and it is super useful. It makes all of electromagnetism relating to plane waves easier. We get to do refraction, reflection. We get to deal with transmission, and surface plasmons come up later, but those are all for other videos, other times. This concludes my take on assignment 4, a wave solution for Maxwell's equations. This is the end. Thanks for watching.